In the first part of the lecture on saturation of nuclear forces, we have discussed three exchange forces, and those forces were Majorana force, Bartlett force, and Heisenberg force. Now, in this second part of the lecture, we will discuss the effects of the exchange forces. But before discussing the actual effects of these forces on saturation of nuclear forces, first of all, I would like to just give a review of the previous lecture. We have studied that the exchange forces were Majorana force, Bartlett force, and Heisenberg force. And as I have told you that Majorana force, in case of Majorana force, there was an exchange of the position vectors, or you may say space coordinates of the two nucleons. As I have considered only a system of two nucleons, so here R1 and R2 are the space coordinates of the first and second nucleon, and in case of Majorana force, these R1 and R2 get exchanged. And in Bartlett force, there was no exchange of space coordinates, only the exchange of, in fact, spin direction take place. And so these spin vectors sigma 1 and sigma 2 get exchanged. And Heisenberg force is actually a general exchange force, in case of which exchange of both space and spin coordinates take place. It means R1 R2 becomes R2 R1, and sigma 1 sigma 2 becomes sigma 2 sigma 1. These all things we have learnt in the previous lecture. Apart from this, we have also learnt the wave equation, or you can say Schrodinger equation, for these three exchange forces. So wave equation, as I have mentioned here, in case of Majorana force is what? This is h cross square by m del square plus e psi of r1 r2 sigma 1 sigma 2, and this equals v of r psi r2 r1 sigma 1 sigma 2. So you can see here these coordinates r1 and r2 gets interchanged. And in Bartlett force, the wave equation is h cross square by m del square plus e psi of r1 r2 sigma 1 sigma 2 equal to v of r psi of r1 r2. You can see there is no exchange of the space coordinates r1 r2, but there is an exchange of the spin coordinates sigma 1 sigma 2 becomes sigma 2 sigma 1. And in Heisenberg force, as both of the coordinates, that is space coordinates and spin coordinates, get interchanged, so equation, or you may say Schrodinger equation or wave equation, is as shown in this equation 3. So these are the facts which we have already studied in the first part of this lecture. Now, in fact, we are going to discuss the second part of this lecture. Actually, the aim of this second part of the lecture is to know the effect of exchange forces. And in this lecture, we will also discuss how saturation property of nuclear forces can be explained in terms of these exchange forces or exchange potential. So now let us start to know the effects of the exchange forces on the property of nucleus, particularly the saturation property of nuclear force. So as I have told you that there are three exchange forces: Majorana force, Bartlett force, and Heisenberg force. And I have already mentioned the wave equations for these forces. Now we will actually discuss these forces in some detail. So first of all, I would like to discuss the first exchange force, which is called Majorana force. Majorana force. As you know, in this case, there is an exchange of the space coordinates, not of the spin coordinates. In fact, in Majorana interaction, it is assumed that the two particles, that is the two nucleons, attract one another if the wave function describing the entire system does not change its sign when the space coordinates of the two particles are interchanged. In this case, this force is in fact attractive, and this force may be repulsive. And when it is repulsive, in fact it is repulsive when the wave function changes sign. And so in case of repulsive interaction, the interaction reflects that the coordinates replaces r by minus r. Vector r is replaced by minus r. So in this case, you can write the wave equation, which I have mentioned in equation 1. See here, this equation under this condition, which I have told you, can be written in a particular form. So in this case, the wave equation may be written as, how we can write this wave equation taking into account the attractive nature and the repulsive nature of the interaction. We can write it as h cross square by m del square plus e psi of r equal to minus 1 to the power L. Actually this is parity. V of r psi of r. Actually this is the most significant form of the wave equation defined in equation 1. Let us say this is equation 1a. You can see from this result that if L is a number, and if this number L is even, in fact this is angular momentum quantum number, and if L is even, then you know minus 1 to the power L will be what? This will be in fact positive. So in this case the parity is positive, and since minus 1 to the power L, that is parity, is positive, so you can say that the wave function psi of r does not change its sign. And if it does not change its sign, then what it implies? Actually this implies that force is always attractive. In this case, always attractive, which I have just mentioned to you, attractive for the states of even L. So you can see from this result that if L is even, then you know minus 1 to the power L, let us say L is 2, that is an even number. So this will be simply 1. L is 4, that will be simply 1. And it means this parity minus 1 to the power L will be equal to positive. And if L, this factor is positive, then psi of R will not change its sign. Psi of R will remain psi of R, and in this condition the force is attractive for all even L, that is when L is 0, L is 2, L is 4, L is 6. In all these cases force will be attractive. Now take the opposite situation. If L is odd instead of even, now we are taking L is odd, then we know that this minus 1 to the power L will be what? When you raise an odd power on minus 1, you will get a negative, you will get minus 1, simply minus 1. And so this will be negative, and this negative value implies that the wave function will change its sign. This implies psi of R changes its sign. And if psi of R changes its sign, this implies that force is always repulsive for all odd value of L. So this implies force is always repulsive for the states of odd L. So you can see that Majorana force may be attractive or may be repulsive. It depends on the value of this orbital quantum number L, and in case of, you can say, even parity, the force is attractive, and in case of the odd parity it is repulsive. Now I would like to give some detail of the another important exchange force, which is actually Bartlett force. So the other, or you can say second exchange force, is Bartlett force. You know, in case of Bartlett force, there is only an exchange of the spin coordinates of the nucleons, not of the space coordinates. And in fact, you have definitely studied that for two particle system, if the total spin is 1, then the wave function is symmetric, and if it is 0, then the wave function is antisymmetric. Just for your convenience, I am writing this statement that for a two particle system, and here we are considering two nucleon system, so this is just a two particle system. Two particle system, if the total spin S is equal to 1, then what will be the wave function? Actually, wave function will be symmetric in this case. Then the wave function is symmetric, and if the total spin of the system is 0, then the wave function is antisymmetric. And so in this condition we can write the wave equation or Schrodinger equation which I have mentioned in this equation 2. So taking the fact which I have just mentioned to you into account, this wave equation 2 can be written in a particular form. So you can say in this condition, equation 2, which is actually the wave equation in case of Bartlett force, is written as this will be h cross square over m del square plus E psi of r, and this equal to minus 1 to the power s plus 1 v of r psi of r. Say this is equation 2a. In fact, this is another form of equation 2a. And you can see from this result that the relation defined in equation 2a to an ordinary potential which changes its sign between s equal to 0 and s equal to 1. So this relation is equivalent to an ordinary potential which changes sign between s equal to 0 to s equal to 1. You can see here, if we take s equal to 1, then minus 1 to the power s plus 1 will be what? This will be minus 1 to the power 2, and this will be positive, and in this case the sign of the wave function will not change. No change in sign. Change in sign of psi of r. But if we take s equal to 0, here there are only two options. So in this case, minus 1 to the power s plus 1 will be what? This will be simply minus 1 to the power 1, and this will be negative. And this negative value of this factor implies that there is a change in the sign of the wave function. So I have mentioned here that this relation is equivalent to an ordinary potential which changes sign between s equal to 0 and s equal to 1. Now, the third exchange potential is known as Heisenberg. You can say exchange force is known as Heisenberg force. And now I would like to give some detail of this very force, that is Heisenberg force. So this is the third exchange force, which is actually a general exchange force. Heisenberg force. You know, in this case, both the space coordinates and the spin coordinates are exchanged between the two nucleons. And you can see, if we will combine the arguments in Majorana force and in Bartlett force, then it is found that for the two nucleon system, if L plus S will be even, then the wave function is symmetric, and if L plus S is odd, then the wave function will be antisymmetric. You can see, because we can treat this Heisenberg force as a combination of the Majorana force and the Bartlett force. Because in case of Majorana force, you know there is an exchange of space coordinate, not of spin coordinates, and in Bartlett force there is an exchange of spin coordinates, not of the space coordinates. But in Heisenberg, in case of Heisenberg force, there is a change of both the space and spin coordinates. So the condition may be just a condition for the Heisenberg force, may be just a combination of the conditions mentioned in Majorana force and in Bartlett force. So in this case, you can say, for the two nucleon system, if L plus S is equal to even, then if L plus S is even, then the wave function is symmetric. This is just a condition, or you may say combination of the Majorana force and the Bartlett force. And if L plus S is odd, then you can say the wave function is antisymmetric. So taking these facts into account, if we want to write the wave equation in case of this Heisenberg force, as you know, the wave equation for Heisenberg force has been defined in this equation 3. So now, taking those two facts into account, this equation 3 can be written in a particular manner. So you can say, in this condition, equation 3 may be written as we can write it as h cross square over m del square plus e psi of r, and this equal to minus 1 to the power L plus S plus 1 V of r psi of r, and say this is equation 3a. And you can see this is just a combination of the equation 1a and 2a. So in equation 1, there was the factor minus 1 to the power L. In equation 2, there was the factor minus 1 to the power S plus 1. And so, as the Heisenberg force is just a combination of those two forces, So here the factor is minus 1 to the power L plus S plus 1. So from this relation, what we can think about the sign of the wave function? You can see if L plus S is odd, then L plus S plus 1, this will be even, because when you will add in the number 1 in an odd number, the resulting number will be even. And if it is even, then minus 1 to the power L plus S plus 1, this will be positive. You can see. And this implies the sign of the ordinary potential is positive. And just we can take the reverse condition. If we take L plus L is even, and if it is even, you can say this L plus S plus 1 will be what? This will be odd, because when we will add 1 in an even number, the result will be an odd number. And if it is odd, you can see this minus 1 to the power L plus S plus 1, this will be actually equal to minus 1, that is negative. And if it is negative, so we can say that the ordinary potential, sign of the ordinary potential is negative. This implies sign of the ordinary potential is negative. So what these results actually refers? Actually, we can conclude from these results that for even L triplet states and odd L singlet states, the force will be attractive, and just its reverse for odd L triplet states and even L singlet states, force will be repulsive. I am just writing this statement for your convenience. So conclusion is that we can conclude from these facts. What we can conclude? The conclusion is for even L triplet and remember, even L triplet and odd L singlet, odd L singlet states, the force will be of what type? Actually, the force will be in this case of attractive nature. Force is attractive, and just its reverse, you can say for odd L triplet states and even L singlet states, what will be the interaction? Actually, in this case, the interaction will be repulsive. So this implies force is repulsive. Force is repulsive. And so we can see that if we consider the 3s state and 1p state, for these states actually potential will be positive, that is potential is simply V of R, and you can say for 1s and 3p potential is minus V of R. Actually, you can see this is actually the even triplet state and odd L state. As here, this is for S subcell, you know L is 0, so this is even triplet state, and for P, L is 1. So this is the case of what? Even triplet, and odd singlet. And here 1s, this is for even singlet. This is even singlet, and 3p, as for this L is equal to 1, that is an odd number, and this is triplet state. This 3 refers the triplet state, this 1 refers the singlet state, here 1 refers the singlet, and here 3 triplet indicates the triplet state. So even singlet and odd triplet. For these, you can see in this case potential changes its sign, and it means force is repulsive, and in this case potential does not change its sign, which refers that force is attractive. So these are some of the important extension of your knowledge regarding the 3 exchange forces. Actually, we should note here that the reversal of sign between 3s and 1s states indicates that the nuclear force cannot be wholly of the Heisenberg type. This is also a remarkable fact. You can't say that nuclear force is completely of Heisenberg nature, Heisenberg type, because the sign of this force just changes. Force or means potential. The sign of the potential just changes when the state becomes 1s from 3s or 3s from 1s. So due to the reversal of sign between these two states, that is 3s and 1s, it indicates that the nuclear force cannot be treated completely like Heisenberg force. This is a very remarkable fact. Now, to develop the theory, to give some more details or more informations, we actually introduce here the exchange operators. Although the Wigner force is not an exchange force, but I have mentioned that force also in this discussion. So actually, including the Wigner force, which is not an exchange force, there we will introduce 4 exchange operators. And what are those 4 operators and what are the important properties of those operators? First we will learn it, and after that we can see what will be the exact form of the most general potential when we will include the exchange force or the tensor force into account. So for exchange operators, exchange operators, we denote by the symbol PW to the operator which is known as Wigner exchange operator. Here W refers Wigner. This is symbol of Wigner exchange operator. Actually, this Wigner exchange operator is an identity operator. An identity operator. It means when this will be operated on a function, the function will not change. It means the eigenvalue will be always 1 of this operator. The another operator is denoted by PM. Here M later is for the word Majorana, and it is known as Majorana exchange operator. Majorana exchange operator. And this operator actually interchanges the positions of the two nucleons. This operator interchanges the positions of the two nucleons. As you know, in case of Majorana force or potential, there is an exchange of the space coordinates. R1 becomes R2 and R2 becomes R1. So the function of this operator is what? Its function is to interchange the position of the two nucleons. It means the position which was occupied by the first nucleon after operating this operator, that position will be of second, and vice versa. Now, the third operator is denoted by the symbol PB. You can understand this B later is for the word Bartlett. So this is known as Bartlett exchange operator. Bartlett exchange operator. And in case of Bartlett exchange force, there is an exchange of spin coordinates or spin directions. So this operator actually exchanges the spin directions of the two nucleons. So this exchanges the spin directions of the two nucleons. Now, the fourth operator is denoted by PH. Again, the letter H is for Heisenberg, and this is called Heisenberg exchange operator. Heisenberg exchange operator. As you know, in case of Heisenberg interaction, there is an exchange of both the space and spin coordinates. So this operator actually interchanges both the position and the spin directions. So this interchanges both position and spin directions. So now we will write the wave equation for the four type of forces in terms of these operators. Actually, in terms of these operators, when Schrodinger equation will be written, then we will simply apply this operator on the wave function, and the result will be in accordance with the nature of the operator. So Schrodinger's equation Schrodinger equations in terms of these operators. The first equation, that is for the equation for the Wigner force, this will be written as Pw is operated on the wave function psi of r1, r2, r3, sorry, not r3, but sigma 1, sigma 2. Sigma 1, sigma 2. As you know, this is an identity operator, and so the result is simply psi r1, r2, sigma 1, sigma 2. The wave equation of Schrodinger equation for Majorana force, we can write Pm operated on psi of r1, r2, sigma 1, sigma 2 will be what? As this operator Pm interchanges the position of the two nucleons. So these r1 and r2 will be just interchanged, and hence our result will be psi of r2, r1, sigma 1, sigma 2. This operator has no effect on the spin coordinates. Now the third equation for Bartlett force will be Pb operated on psi r1, r2, sigma 1, sigma 2. As you know, this operator interchanges the spin directions, so our result will be psi of r1, r2, but sigma 2, sigma 1. You can see there is an exchange of the spin vectors sigma 1 and sigma 2 here. Now the fourth equation for Heisenberg force, this will be Ph operated on psi r1, r2, sigma 1, sigma 2 will be what? As this operator interchanges both the position and spin directions, so our result will be psi r2, r1 and sigma 2, sigma 1. So in terms of these four operators, We have just mentioned the Schrodinger's equation or wave equation. Now, you must see these wave equations, and from these wave equations we can easily find some properties of these operators. You can see here from these equations you can see this PW is equal to 1, and in fact this is an identity operator, so this is equal to 1, or you may say I also, identity matrix you may say. And the another important property is pH. You can see here pH is actually the product of PM and PB. You can see if we will operate this operator on the wave function, so first of all we will take the operation of PB on the wave function, which will interchange sigma 1 sigma 2, and after that we will take the operation of this much, and you can see that result will be just like this. So we can see this. I am just writing it here. Let us say we operate the operator PMPB on the wave function psi of R1, R2, sigma 1, sigma 2. You know, to take this operation into account, first of all we will operate this operator PB on this wave function. So our result will be PM, and effect of this operator PB is what? Its effect is actually to interchange the spin coordinates. So this will be PM psi of R1, R2, sigma 2, sigma 1. Now, when this operator PM is operated on this wave function, what will be our result? Our result will be, you see the above result, psi of R2, R1, sigma 2, sigma 1. And you can see this is actually equal to this much. So we can write that therefore we can write PM PB psi of R1, R2, sigma 1, sigma 2 is equal to what? This is actually equal to pH psi R1, R2, sigma 1, sigma 2. And this implies that this pH is equal to PM into PB. So this is an important property, or you may say this is a relation between these three exchange operators. Now we can also see that the square of PM, we should write here M as superscript PM. This will be actually equal to a square of PB and this is equal to a square of pH, and all these three are equal to 1. It means how we can explain this. I am just explaining any one, and you can see that if we apply this PM square is applied on the wave function psi r1 r2 sigma 1 sigma 2, then we can write it as PM psi of r1 r2 sigma 1 sigma 2. And what will be this? We know when this operator will be operated on this wave function, the result will be psi r2 r1 sigma 1 sigma 2. And now again this operator is operated on this, so what will be the result? The result will be psi r1 r2 sigma 1 sigma 2, because this operator interchanges the position coordinates r1 and r2. And if the result is like this, so you can say that the eigenvalue of this operator PM square will be equal to 1. And in a similar manner, you can prove that the eigenvalue of PB square and PH square is also 1. So therefore, we can say this PM square is equal to 1. It means its eigenvalue is equal to 1, PM square. And if its eigenvalue is 1, in that condition, the eigenvalue of the operator PM or PB or PH will be actually plus minus 1. It is very easy to see here that in the similar manner, as I have told you, you can see this PB square will be equal to PH square, and all these will be equal to 1. And so it means PB equal to PM equal to you cannot write it in this manner, but we should say that I am just writing it in another page, that the exchange operators PM, PB and PH have only two eigenvalues. And what are those eigenvalues? Those are plus 1 and minus 1. Plus 1 and minus 1. So these were some of the important properties of these four operators. Particularly, we have discussed in detail the exchange operators PM, PB and PH. Now, on the basis of all these discussions, we can write the most general form of the potential of the exchange type. So now we are in a stage to write down the most general form of the potential, actually including the exchange forces into account. So the most general potential of the exchange type can be given as, we will write this V is actually V of R, and this will be equal to VW of R. As you know, this is Wigner potential and it has no exchange character, and so in the first term there is no exchange operator. And if we will write even PW operator in front of it, that will make no change, because you know PW is actually an identity operator. So in first term we do not write the operator, and plus Vm, this is Majorana potential of R operator Pm. In fact, this Pm refers that this potential may be positive or may be negative in accordance with the eigenvalue of this operator, and plus Vb, this is Bartlett potential of R Pb, and plus Vh of R, this is Heisenberg potential Ph. And what will be our equation number? You can see I have just mentioned equation up to 3. So this will be our fourth equation. Let us say this is equation 4. Here one thing is very important, we should note that the tensor force may or may not have any exchange character. It means tensor force may have exchange character and it may not have an exchange character. Both facts are true. Actually, the tensor force operator, which I have mentioned in the earlier lecture and by a symbol S12, actually this operator, which is known as tensor force operator, commutes with the Bartlett spin exchange operator. And if it commutes with this operator, then what we will get? So you can see that the tensor force may or may not be of exchange character. And another remarkable fact is what? Another remarkable fact is the tensor force operator S12 commutes with Bartlett exchange operator. And when you say that this S12 operator commutes with Bartlett exchange operator, that is PB, then what actually we are saying? We say that the commutator of S12 with PB is equal to 0, and this implies S12 PB minus PB S12 is 0. That is, you can say this S12 PB is equal to PB S12. PB S12. In fact, only there are two types of tensor forces. First one is actually called ordinary tensor force, and you can say this ordinary tensor force as Wigner force 2, and this Wigner tensor force has no exchange character. But the second tensor force, which is known as Majorana exchange tensor force, or you can say that this tensor force has Majorana exchange character. And so the Wigner tensor force is not of exchange character, but the Majorana tensor force is of exchange character. So if we will also include the exchange tensor potential, then the most general form of the potential of exchange type will also include the term in which this tensor force operator S12 will be included. So if we include the exchange version of the tensor force, then the general form of the potential is given as, in this condition, this V is actually equal to, this V will be equal to what? All the terms previously in our equation 4 will be contained in this equation 2, but apart from that, we must include the potential term which have actually tensor character, or you may say that tensor force character. So we write this expression as VW of R plus Vm of R Pm plus Vb of R Pb plus Vh of R Ph. All these terms was already present in equation 4. Now we are actually considering here the exchange characters potential. So two terms will be surplus here. Thus, these terms are VTW of R S12 and plus VTM of R S12 PM. Say this is equation 5. In this equation you can see up to this term the equation is same as equation 4. Now what are these two potentials, VTW and VTM? Actually these are not pure potential but a mixture of two potentials. You can say here this VTW of R. Actually this potential term refers the mixture of Wigner and tensor potential. This is mixture of Wigner and tensor potential. T later is here for tensor and W for Wigner. And like that, this VTM of R, this actually refers the mixture of tensor and Majorana potential. Mixture of tensor and Majorana potential. So this is actually the form of the potential in general form of potential when we include the exchange potential regarding the tensor forces. Now after this discussion of the exchange forces and exchange potential, we are in a stage that we can explain the saturation of nuclear forces in terms of these exchange forces, or you can say exchange potential. So now our aim is to know the condition for the saturation of nuclear force in terms of these exchange potentials. So you can say now we are going to discuss exchange force and saturation property. Exchange force and saturation. Actually, the Bartlett spin exchange force does not lead to a saturation of the binding energy per nucleon. If the nuclear forces are of Bartlett type, the heavy nuclei will exist with all spins in fact aligned in same direction. And because we do not consider the tensor force in that case, so all spins are aligned. And if the all spins will be aligned in a nuclei, let us say of mass number A, then the number of interacting nucleons, or you may say the number of pairs of interacting nucleons will be what? That is simply A into A minus 1 divided by 2, where A is its mass number. So you can say the most remarkable fact is that the Bartlett spin exchange potential does not lead to saturation of binding energy per nucleon, because if we will want to explain the saturated value of binding energy per nucleon, which is almost 8 mega electron volt per nucleon, we cannot succeed, because you will see that if we consider the Bartlett spin exchange potential only, then binding energy per nucleon should increase with increase in mass number. For larger mass number, for the nuclei with larger mass number, binding energy per nucleon should be larger, and for a smaller it should be smaller. But how? Since in this case all spins of a heavier nucleus are aligned. So if A be the total number of nucleons, then the number of interacting pair of nucleons will be actually equal to what? This will be A into A minus 1 divided by 2. And so you can see that the interacting nucleons pairs number is this much. So in this case, binding energy per nucleon, Be over A, will be proportional to A, and hence you can say that the binding energy per nucleon is A dependent. But it is A dependent when you say only when you try to explain this binding energy per nucleon in terms of the Bartlett spin exchange force potential. But so we can say that this saturation property of the binding energy per nucleon cannot be explained in terms of the Bartlett spin exchange potential or force. Actually, the space exchange in Majorana potential or force and in Heisenberg force leads the saturation of binding energy per nucleon. So you should note that saturation of binding energy per nucleon, Be over A is due to the space exchange of Majorana and Heisenberg forces. Actually, to get the idea of binding energy per nucleon is saturated, to get the idea of this very fact, I am just writing an expression for the average value of potential. In fact, this expression is due to uh, the two scientists Bartlett and Wiskopf. I am just mentioning their result. I am not deriving it. The derivation of this result is a subject matter of another lecture. I am just giving the reference of the potential as calculated by two scientists, Bartlett and Wiskopf. And in terms of that expression for average potential, we can discuss the condition for the saturation of the binding energy per nucleon. So, according to Bartlett and Wiskopf, average potential V is given as A by 2 into VW minus Vm by 4, this is 4, minus T square by 2A into Vm into R naught by capital R naught whole to the power 3 into 1 minus 9 over 16 R naught, small r naught, divided by R naught A to the power 1 by 3 and plus 1 over 32 R naught cube over capital R naught cube into A. Actually, this is 3. As I have told you, this result is due to two scientists, Bartlett and Wiskopf. I have not explained or derived this result, and you should remember it here. For the present context, we must remember it. And say this is just a result A, because this equation is not from our calculation. So I have just changed the equation number. This is just a reference from the work of Bartlett and Wiskopf. And in this expression, what the different term refers, you know the meaning of several potentials here. VW, Vm are in fact the Wigner potential and Majorana potential, but the new terms which have been used in this, I am just giving the meaning of those terms. You can see this R naught is actually a range of the nuclear force. This is a range of the nuclear force, and you know the radius of a nucleus, R is radius of a nucleus. This is given by the expression R naught A to the power 1 over 3. And in this expression, this capital R naught is actually a constant. Its value is 1.2 Fermi or femtometer. And the term T is what? Actually, this is defined as 1 over 2 n minus z. Here n is number of neutrons in the nucleus and z is actually number of protons. So this n minus z is actually excessive number of neutron over proton. In fact, in the nuclei of higher mass number A, always n is greater than z. So this will be just a positive quantity, or you may say positive number. Now see this equation, and if all the terms which have a smaller value in this equation A are neglected, then this equation A will be written in a very simple form. So you can say, if a small terms in A are neglected, then equation A is given as, we can write this equation as V, average value of V is approximately equal to, because we have taken this consideration that small terms are negligible, so here is approximation sign. This is in fact equal to minus AB into A plus AS into A to the power 2 by 3 and plus C1 T square by A, and say this is equation B. Actually, these coefficients, that is AB, AS and C1 can be defined from the equation A. You can see what will be the values of AB, AS and C1 in equation A. Now you can see this first term in equation A. In equation A, this is the first term, and this first term in this equation must be negative. Why you say that it must be negative? Because we know that both the Wigner potential and the Majorana potential, both of these potentials are in fact negative. And if this should be negative, in that condition, what should be the relative values of Vm and Vw? We can see from this equation that you should note that the first term is negative because I have told you that both the Wigner potential Vw and the Majorana potential Vm are negative. And we can see from that equation A that for a positive value of AB, what should be the relative values of Vm and Vw. So you can see first term in A is negative, and for positive value of AB, you can see that AB has been written at the place of what? AB has been written at the place of, you can see, in fact this has been written at the place of VW minus Vm by 4. VW minus Vm by 4. So this AB will be positive only when VW is greater than Vm by 4, or you can say this Vm by 4 is less than VW. So for positive value of AB, what will be the necessary condition? As these potentials may be negative, so we write the condition in this form, that modulus of Vm is less or equal to 4 into modulus of VW. Actually, this result is the condition for the saturation of the binding energy per nucleon for all A. In this result is in fact independent of A. So for nuclei of any mass number, the saturation of binding energy will take place, or it is saturated, because Vm is less or equal to 4 VW. So this is condition of saturation of binding energy per nucleon. Binding energy per nucleon. And from this result, you can see that the Majorana force must contribute at least 4/5 of the attraction, and the Wigner force in comparison is rather small, and it contributes no more than 1/5. So this is also a very remarkable fact. So I hope you have clearly understand the ideas regarding the exchange forces and the explanation of saturation of binding energy per nucleon in terms of exchange forces or exchange potential.